Consider the example. Solve the reference relation. Solve the reference relation Fn is equal to 3 times of Fn minus 1 plus 2. Here n is greater than or equal to 1 and F0 is equal to 1 by using generating function. There is no much difference between this problem and the last problem. Only difference is this too, how it affects our solution. Now from given relation, Fn is equal to 3 times of Fn minus 1 plus 2. Take it number 1. Then we consider our generating function gz sigma n varies from 0 to infinity. Fn zn is equal to f0 plus f1z plus f2z square plus so on. Take it number 2. Then multiply both sides of 1. Multiply both sides of 1 by z raised to the power n. We get Fn into z raised to the power n 3 times of Fn minus 1 into z raised to the power n plus 2 into z raised to the power n. Then we substitute the variation, that is put n is equal to, here variation is 1 to so on, 1, 2, 3 and so on, and sum up. Directly we write that is equal to sigma n varies from 1 to infinity Fn Zn is equal to 3 times sigma n varies from 1 to infinity Fn minus 1 into z raised to the power n plus 2 times sigma z raised to the power n. In the last term, it does not contain any f. Now say take it number 3. So we can solve each term separately or simultaneously. Let's start with the left hand side. That is sigma n varies from 1 to infinity Fn z raised to the power n. That is equal to substitute for n starting from 1, 2, 3 and so on. If we put n is equal to 1, it is f1 z1 plus f2 z2 square 4 n is equal to 2 plus so on. Now we compare it with number 2. It is our generating function f1z. It means this bracket starts from this part. The remaining part is, that is g z minus f0. For this first term sigma n varies from 1 to infinity Fn minus 1 into z raised to the power n. Put n is equal to 1. If we put n, it will be f0 z raised to the power 1 plus f1 z square plus so on. Now if we compare it with the given generating function too, we see f0 is unknown, f1 is with z. No, here we can take z common. f0 plus f1z plus so on. That is equal to z. No, this bracket is equal to totally right hand side of the generating function, that is equal to g z. No, for sigma z raised to the power n, that is equal to, if we put Zn is equal to 1 to 3 sigma n varies from here 1 to infinity, sigma n varies from 1 to infinity, z raised to the power 1, z raised to the power 2 plus z raised to the power 3 plus so on. If we take z common from this, we get 1 plus z square plus z cube plus so on up to infinity. So see how this constant term which is in addition or the subtraction affects the calculation in a generating function. No, this too is converted into this according to given condition. No, we see in the bracket it is the geometrical progression from 1 to infinity, and we know the solution for the in the geometrical progression, solution for sum to infinity, sum to infinite terms, that is equal to a upon 1 minus r, where a is the first term and r is the common ratio of two consecutive terms. In this you can see here a is equal to 1 and r is equal to z. Z upon 1 z, z square upon z, z cube upon z square again z. That is equal to sigma n varies from 1 to infinity into z raised to the power n is equal to z into a1 divided by a upon 1 minus r, a upon 1 minus z. It is the expansion of this sequence which is converted into the geometrical progression. Now we compile all the three terms by using number 3. From 3 we put all the values for this, that is g z minus f0 is equal to 3 times. For this we get z into g z plus 2 times z upon 1 minus z. Now according to the given initial conditions, it was f0 is equal to 1. By using f0 is equal to 1, it is g z minus 1 is equal to 3 times of z into g z plus 2z upon 1 minus z. Now we bifurcate the terms. Here g z minus 3 times of z into g z is equal to 1 plus 2z upon 1 minus z. Here gz is the common, 1 minus 3z is equal to 1 minus z is the LCM, 1 minus z plus 2z, that is equal to 1 plus z divided by 1 minus z. That is, we get the generating function from here, that is equal to 1 plus z divided by 1 minus 3z into 1 minus z. It is the generating function for the given recurrence relation. No. But we want to solve it further. No. What is the problem? Here we transfer, if we transfer both these brackets to the numerator, then we will have to apply the binomial theorems. That will create a very difficult calculations. To avoid such confusion, we use here the another concept of the basic algebra, that is the partial fractions. Before we solving this, we will have to apply the partial fraction on this generating function. Let us see, we take the right hand side. We are discussing about the partial fraction. It is in addition to the topic we are discussing. That is 1 plus z divided by 1 minus 3z into 1 minus z. Here there are two linear factors, 1, 2. Both are different. Similarly, in this way, there may be the three linear factors non-repeated. We say non-repeated. We write it a upon 1 minus 3z plus b upon 1 minus z. A and b are some constant. A upon first factor. First, who is first? Whichever may be the first. Then we multiply the denominator and numerator, multiply both sides by 1 minus 3z into 1 minus z. That is the denominator of the left hand side. We get 1 plus z is equal to a into 1 minus z plus b into 1 minus 3z. And we consider it, say, number 4. After that, we consider the factors separately like this. Put 1 minus 3z is equal to 0. This implies z is equal to 1 by 3 in 4. Here we put the value of z. It means 1 plus 1 by 3 is equal to a into 1 minus 1 by 3 plus this is 0, because we have considered 1 minus 3z is equal to 0. That's 4 by 3 is equal to a into 2 by 3. Thus we get a is equal to 2. No, we have another factor, 1 minus z. Put 1 minus z is equal to 0 in, or z is equal to 1 in number 4. Here we put z is equal to 1. On the left hand side, that we see 1 plus 1, it will become 0, because we have put 1 minus z is equal to 0, 0 into a, again 0. No, plus b into 1 minus 3, that is 2 is equal to minus 2b, therefore b is equal to minus 1. No, it is a necessary, rather it does not belong to the it does not belong to our topic reconciliation, but to solve the reconciliation we have to use the different tools available in the algebra as we used previously. Geometrical progression for infinite series. Here we have used the partial fraction of the type where non-repeated linear factors exist. There may be 2, there may be 3. Now we change the generating function, or we can write this generating function, say gz is equal to this is equal to this, and this is equal to this. Here value of a is 2. 2 upon 1 minus 3z sine plus b minus 1. That is minus 1 divided by 1 minus z. That is 2 upon 1 minus 3z minus 1 upon 1 minus z. Now we can see it is easy for us to transfer these denominators to the numerators and then applying the binomial theorem. So we can write it 2 into 1 minus 3z raised to the power minus 1 minus 1 minus z raised to the power minus 1. We can apply binomial theorem at this factor and separately at this factor. That is equal to 2 into 1 plus 3z plus 3z square plus 3z cube plus so on minus 1 minus z means 1 plus z square plus z cube plus so on. This is the binomial theorem we applied for the negative index. Then that is equal to 2. It is also a sequence. 1 means, see, as we discussed previously, it means 1 is equal to 3 raised to the power 0. So we can write it in this way: sigma n varies from 0 to infinity 3z raised to the power n. If we put n is equal to 0, we get the first term. Put n is equal to 1, we get the second term. Similarly, here it is expansion of z varies from 0 to infinity z raised to the power n. That is z raised to the power n. We can solve it in this way. Variation is same for the both terms. Variation is same for the both terms. We can write in this way: n varies from 0 to infinity 2 times of 3 into z raised to the power n minus z raised to the power n. It means we can combine both the terms because the variation in the both sigma, it is same. That is equal to, on the left hand side it was generating function gz is equal to sigma n varies from 0 to infinity. We take z raised to the power common and in bracket we get 2 into 3 raised to the power n minus 1. No, we know what is the generating function sigma n varies from 0 to infinity fn z raised to the power n, that is equal to sigma n varies from 0 to infinity z raised to the power n bracket 2 into 3 raised to the power n minus 1. Compare both sides. Compare both sides. See, each thing is common. You see, this, expect this, f of n is equal to 2 into 3 raised to the power n minus 1. That is the final solution for the recurrence relation. Rather, it's hard, it will take time, but that is the actual situation when we have to solve such recurrence relations with the help of the generating functions.